Good afternoon, guys. Hope you're doing well, and welcome back. This is our second lecture for Chem 111. This is going to be the acid-base lecture, so we'll get started talking about that. I'm going to share my screen with you guys so that we can walk through this together. Okay, so things we're going to be talking about today. Definitions of acids in terms of Arrhenius, Bronsted-Lowry, and eventually Lewis. We'll be talking about that. Acid-base properties of water and the autoionization of water. pH, which is a measure of the acidity. Strengths of acids and bases. Weak acids and acid ionization constants. Weak bases and base ionization constants. And the relationship between the ionization constant of acids and their conjugate bases. So those are the topics that we're going to get to today, and this is all out of chapter 15. All right. So definitions that you'll need to know, understand, and work with. So these are actually defined, a lot of them, in chapter 4, but we're going to be using them here. So we're going to be talking about Arrhenius, Bronsted-Lowry, and Lewis. We're going to be talking about, and those are types of acids and bases. Amphoteric, what that means. Conjugate, what that means. Binary, oxoacids, and carboxylic acids. So those are terms that will become familiar with you by the end of this lecture. So a few types of acids and bases. So we have the initial definition of acids and bases, which is from Arrhenius. An acid, when dissolved in water, produces H plus and therefore increases the pH, the H3O plus concentration. A base, when dissolved in water, produces OH minus and therefore lowers the pH, i.e. the H3O plus goes down. So that's the first definition that we dealt with, and that's from Arrhenius. Then Bronsted-Lowry came in and said, wait, there are other things that behave in similar ways, but they don't affect the OH minus concentration. So we still have acids defined as an H plus donor, but we now have bases defined as an H plus acceptor. Okay, I will also refer to this as BL. There's another definition that we're going to get to, and it's called Lewis. In that case, an acid is an electron pair acceptor, and a base is an electron pair donor. Now, on Bronsted-Lowry acids are also Lewis acids. Bronsted-Lowry bases are also Lewis bases. Some materials that are Lewis acids are not Bronsted-Lowry acids, and some materials that are Lewis bases are not necessarily Bronsted-Lowry bases. So anything that's a Lewis acid will be a proton donor, and therefore fits the Arrhenius, Bronsted-Lowry, and Lewis definitions. Anything that's a Lewis base as an electron pair donor probably can accept protons too, and probably leads to OH minus, but that's not always the case. So those are the definitions that we have. Awesome possum, right? Here's a table for you, because I find tables are easier for me. So the type of acid, Arrhenius, Bronsted-Lowry, or Lewis, whether they're acids or bases, how they're defined, and the H plus, what happens to it up or down, the OH minus, what will happen to it up or down, and do they fit by any other definition? Okay. Questions, comments, problems? Hopefully none, but that's the information that in table form. Now, let's talk about conjugate acid-base pairs. So a lot of this talked about proton donation and proton acceptance and things like that. And so we often talk about conjugate acid-base pairs as being one with a proton and one without a proton. So HNO2 is nitrous acid. I can remove the H from that to give me NO2 minus, which is its conjugate base. So that is a conjugate acid-base pair. Here, water is acting as a base. It reacts with the H plus that came from HNO2 and becomes H3O plus. So the base has a conjugate acid with the H plus added to it. So that's a conjugate acid-base pair. And we typically don't talk about conjugate acid-base pairs in terms of Lewis acids, so electron donors and things like that. We typically only do it for the addition or subtraction of a proton. You may be asked, which of these are conjugate acid-base pairs? what is a conjugate base of this acid. If you're going to make a buffer, you need to be able to add a conjugate base to it. So you'll need to have, in this case, you need to have a salt that contains the NO2 minus. All right. So there are times when we're going to need to be able to deal with those conjugate acid-base pairs. They have practical implications that we need to be able to deal with. Bear with me just a moment. Sorry about that. So that is how we're going to need to be able to talk about it. Now, let's talk about something that really bothered me when I was a student. We talk about removing H plus, adding H plus, H plus, H plus, H plus, H plus. So we have H plus running around in solution? No, we don't. We always refer to this as H plus donors and acceptors. But we don't have H plus alone in a solution. It always attaches to something else. And in water, it always binds with water to make H3O plus. Now, why is it that we refer to it both ways? Mostly because chemists are lazy. So we don't always list the water that's with it. Sometimes we'll list it as H3O plus, sometimes we'll list it as H plus. It goes both directions. And it depends on the chemist and the situation, which one it gets done, right? But these two things are equivalent, and you need to understand that. If you go out onto the internet to seek somebody else's definition of these things, then you may see something different than what I talk about. So that's why you need to know that, okay? Now, water is special. I always tell my students in 110 that water is very special. It has lots of different properties. We can write it here as H-OH. Why did I do that? Because water has one acidic proton, the one that's listed in red, and then the OH group, which is a base. It can act as both an acid and a base in both Arrhenius and Bronsted-Lowry definitions. So it's a proton donor. It also donates OH minus for the Arrhenius case and accepts the proton in the Bronsted-Lowry case. That makes water amphoteric. Okay, the amphoteric substance is one that can donate or accept H plus ions. It can be either an acid or base. It's also amphiprotic, meaning it can donate or accept. So both of those are terms that you will hear used with that. We can look at NH3 plus H-OH goes to NH4 plus OH minus. Okay, so that's what we're talking about there. So the water donates a proton to become OH minus, which is in itself a base. That means that water, OH, and OH are a conjugate acid-base pair. They differ by only one proton. You should be able to predict the conjugate base of an acid or the conjugate acid of a base and identify them in a drawing. This is called the autoionization of water. So two waters acting together give me an OH minus and an H3O plus. Now remember what we talked about last time. What's the K for this? Now Kw is OH minus times H3O plus, which is equal to 1 times 10 to the minus 14th at 25 degrees. Most of what we talk about, we assume is at 25 degrees. Now that K, that temperature, that value for K is dependent on the temperature. So just in the same way that you can use it, this value for K, you can use other values for K to do the same things. You just have to remember that it's a different value and a different temperature, okay? The pH scale. All right, pH is a short way to report the H3O plus concentration, and that is defined as pH equals the negative log of the H3O plus concentration. Awesome, I know mathematically how to find it. If a solution is neutral, H plus equals OH minus, and the pH is 7. If a solution is acidic, the H plus is greater than the OH minus, and the pH is less than 7. If a solution is basic, H plus is less than OH minus, and the pH is greater than 7. Okay, so that's what we're talking about there. Now, in every case, we still have H plus times OH minus is 1 times 10 to the minus 14th. But if the H is larger than the OH minus, then consequently it has to be smaller. Okay, so that's relationships there. POH is a short way to report OH minus. So again, POH is defined in the same way as pH, except it's for the OH minus concentration. So if a solution is neutral, the H plus equals the OH minus. Your pH equals 7 and your pOH equals 7. If your solution is acidic, your H plus is greater than the OH minus. That means your pH is less than 7 and your pOH is greater than 7. They're opposites of each other. Okay. If the solution is basic, the H plus is less than the OH minus, pH is greater than 7, and the pOH is less than 7. If we take the negative log of both sides of the Kw expression, we get the negative log of H3O plus the negative log of OH minus is equal to the negative log of 1 times 10 to the minus 14th. We know that that first expression is pH. The second expression is pOH. And if I take the negative log of 1 times 10 to the minus 14th, I get 14. So pH plus pOH equals 14. As an aside, when we measure pH either with pH paper indicators or pH meters, indicators are one color at certain pH and another color at other pHs. And that's related to the K of the acid-base system. All right. So that's what we're talking about there. And that's why we get this lovely little expression that pH plus pOH equals 14. One of the reasons that I bring it up here is because we are assuming when we use that we are at 25 degrees. If we are not at 25 degrees and this value changes, then this value right here has to change too. So there are implications to that. All right. Now, remember this? We call this the fun box. If I know the concentration of H plus, then I can find the concentration of OH minus by dividing Kw by the H plus. Now, even if this Kw is different at that temperature, I can do it this way. This is to find this one for 25 degrees. So that's the OH minus concentration. Conversely, if I have the OH minus, I can get to the H plus again through Kw. So if I have the H plus and I take the negative log of that, I get the pH. If I have the pH and I take 10 to the negative pH, that gives me the H plus concentration. pH and pOH are related through this equation, so I get the pOH is equal to 14 minus the pH, or pH is 14 minus pOH. And if I'm down here in pOH, I can find the OH minus by taking 10 to the negative pOH, or pH equals the negative log of OH minus. Okay, so we should be able to go all the way around with this and do this. All of these things that we're looking at here, both the top and the bottom, depend on Kw being the value of 1 times 10 to the minus 14th. If it's still if it's a different value, if we're at a different temperature and you get a different Kw, you can substitute that Kw in here and still use these expressions. Okay, you just have to remember that you need a different K to do that. All right? So that's that. Now we've defined our acids, we've defined our bases, we've defined pH and pOH, we've talked about H3O plus and OH minus, yada, yada, yada. We know how to use that. Oh, and the fun box will be on your test. So we should be able to get between all of those things. If you have struggles getting between H plus, pH, OH minus, and pOH, do a lot of practice, okay? Use that box, try to understand how you get between them. It should become second nature to you. When we talk about acids and bases, we need it all the time. So that's something that we need to be able to deal with. Now, strong acids and bases in solution, they are product favoring reactions with large K values, meaning that the acid is almost completely ionized, right? So in the past, we've said that there is no K value for certain things because it goes almost all the way to completion. That's what we're talking about. If it goes almost all the way to completion, then I have a really, really tiny number as my reactant, and that becomes undefined. So K values are either really huge or undefined. Okay, if it's undefined, that means it's almost completely ionized. This is therefore not a reversible reaction, and Ka and Kb are undefined in this case. Okay, for strong acids, the H3O plus is equal to the HA concentration. We assume that it's 100% dissociated. Okay, strong bases are almost all of the metal hydroxides, and the OH minus is going to be equal to the OH concentration. Okay, or 2 times the concentration of the MOH2. So depending on if it's a single OH minus or a double OH minus, that will determine your concentration for that. Okay. Well, we talked about strong acids. Now, what's a weak acid? Anything that's not a strong acid is a weak acid. That means that we have a partial ionization that goes on. Some of it stays as the acid, HA. We call it HA. So it's H plus and the ion, A minus. So it stays as HA, and some of it goes to H plus plus A minus. Okay, so that's what we're talking about right here. This is the reaction that we're looking at, is the dissociation of the acid to give us the H plus and the A minus. The Ka is going to be defined as the H plus times the A minus over the HA. The value of pH is related to the value of K. The more the reaction favors making H3O plus, the lower the pH will be, and the higher the pOH. So larger K values are stronger acids. In order for that to happen, the following conditions must either exist or help. Weak bonds between H and A means that this goes forward. So if it's easy to pull that H plus off because of the structure, then that's a good indication that it's going to be a strong acid. If A minus is a really good anion on its own, it can hang out and be fine, then that helps that process. It means that it's going to be a stronger acid. And the HA bond must be polar, and the more polar, the better. So the more polar it is, the easier it is to pull that H plus off. Okay. Weak bases. Anything that is not a strong base is a weak base. Awesome. So I have a base plus water. I pick up the proton to get BH plus, and I have OH minus left. That means my Kb is BH plus times OH minus over B. The value of pH is related to the value of K. The more the reaction favors making OH minus, the lower the pOH will be, and therefore the higher pH. Larger K values are stronger bases. That's what that should say. And in order for that to happen, we need to have the ability to pull that metal ion away from those OHs. Okay. The more stable the metal ion is, the M plus or the M2 plus, that's going to be better. And the MOH bond must be polar in order for that to happen. Okay. So those are the things that we talk about there. Now, Rice tables for acid equilibrium. Oh Lord, we talked about these last time. They still appear here. We can still use them to solve these equations. So if I have HF, which is a weak acid, it goes to H plus and F minus, all right? The Ka for that is 7.1 times 10 to the minus 4. We also know that the Ka is equal to the X for the H plus and the X for the F minus times the concentration of HF, or over the concentration of HF. So in this case, there are two ways that we generally solve this. One, we can assume that X is small. If we assume that X is small, we substitute the concentration of HF for the 0.5, or the concentration minus X. So rather than putting this in the bottom of this expression, we just put in the concentration of HF. We then multiply Ka times that HF concentration. Then X squared is equal to that multiplication, and X is the square root of that. So that's the value that we get when we make the assumption. The other way that we can do this is solve it through the quadratic equation. So we actually use this expression here. We end up with X squared over 0.5 minus X equal to 7.1 times 10 to the minus 4th. That gives me X squared plus 7.1 times 10 to the minus 4th X minus 3.55 times 10 to the minus 4th, which is equal to 0. I then use the quadratic equation to solve for my two values. The only one that makes any sense, i.e. the positive value, is 1.81 times 10 to the minus 2, which is almost the same as what I reported here. When we have a value for X, we can test the assumption that X is small. So once I have this value that I've solved for X, I can test if it's small. And the way that I can do that is I divide this by the initial concentration and multiply by 100. So if it's less than 5%, then it's a good assumption and we can use that. Otherwise, we need to use the quadratic equation. So I usually solve for X in this way. check to see that it's less than 5%. And if it's not, then I go over here. Okay. So that's how that works and what we need to do with that. Questions, comments, problems? Hopefully not, but there we are. Conjugate acid-base pair. Let's talk about our conjugate acid-base pair. If it's a strong acid, like HCl, then the conjugate base is Cl minus. That conjugate base is a weak base. Okay, so if it's a strong acid, I have a weak base. In aqueous solution, H3O plus is the strongest acid that can exist. Any other strong acids give their protons to the water to produce H3O plus. The OH minus is the strongest base that can exist in water. All strong bases react with water to produce OH minus. Okay, so that's the strongest you're going to see in either of those cases. Awesome. You can see these scales. Now, sometimes you'll get these scales. These are the strong acids because they're above H3O plus. So HCl, H2SO4, HNO3 are strong acids. These are going to be weak acids. And once we get below H2O, we see negligible activity acting as an acid. Okay, so these don't really act as acids. But these guys in between H2O and H3O plus, they act as weak acids. On the base side, we have these being negligible basicity. So once they come off, once they've lost that proton, they don't really act as bases in solution. So anything that's above on the base of the H2O on the base scale doesn't really do anything. Anything that's between H2O and OH minus, these are our weak bases. So these are bases that can pick up protons that then have a Kb associated. These are our strong bases. So O2 minus, H minus, and CH3 minus react with water to produce OH minus. So these are our strong bases. These are going to have very large Kb values, and therefore they're going to be considered completely dissociated. All right? So that's what this little diagram means to you. Your weak acids and weak bases are here in the middle. Anything that's above this line is strong. Anything that's below this line is strong for the acid and the base. Okay? All right. Now, what's the relationship between Ka and Kb? Ka is an acid dissociation constant. Kb is a base dissociation constant. So let's consider the reaction for acetic acid, CH3COOH, going to H plus CH3COO minus. The Ka for that is H plus times CH3COO minus over CH3COOH. Awesome. Remember that acetate ion reacts with water in the following reaction. So water can react with the acetate ion once I've made it. This guy right here can pick up a proton from H2O to go back to CH3COOH and generate OH minus. The Kb for that expression is CH3COOH times OH minus over CH3COO minus. So I have these two expressions. And if I multiply them together, I have H plus times CH3COO minus over CH3COOH times CH3COOH OH minus times CH3COO minus. So the CH3COO minus cancels. The CH3COOH cancels. And I'm left with H plus times OH minus, which is Kw. So that means that I have the definition of Kw. As long as I know what that value is, I can divide by the Ka. So divide Kw by Ka, and that will give me Kb. If I have Kb, I can go the other direction. Okay, so there is a relationship there that we can work with. All right, next topic after questions. We're done for today. Woohoo! Nice short lecture. So hopefully you guys have no questions about our acid-base definitions. That's what we're doing in terms of acid-base definitions. Now we're going to start using acids and bases to do things as we move forward into the next couple of lectures. But that's how we define our acids and bases, and hopefully you're good with that. If you're not, questions, comments, problems, please let me know either via email, via phone call, or in my office. Just come on by, say, hey, I had a problem in, the acid base lecture. You were talking about this thing right here, and I didn't understand, or I thought, or whatever. Okay, so that's how that's going to work. And that is everything for the acid base. So I'm going to say goodbye for now. I will see you later when we record our next lecture. Thanks, guys.